Good morning. Hi, my name is Lisa Heithmar. I am, as he said, with the Rutgers Forestry Club. I'm studying ecology, evolution, and natural resources. This presentation is on tropical cyclones and sea level rise impacts on old-growth maritime forests in New York and New Jersey. Dr. Nicole Davi is an adjunct senior research scientist at the Tree Ring Laboratory at Lamont Doherty Earth Observatory and a professor and chair of the Department of Environmental Science at William Patterson University. Dr. Davi's research focuses on developing and interpreting high-resolution paleoclimatic records in order to further our understanding of climate change over the past 1,000 years. Currently, she is building a field program focused on northeast coastal forests with the aim of reconstructing tropical cyclone frequencies and severity recorded in these unique maritime forests. Please welcome Dr. Nicole Davi.
Good morning. Thank you, Lisa. Thank you to the New Jersey Shade Tree Federation for inviting me, being interested in the research that I'm doing. Just waiting for my slides to come up. Like Lisa was saying, my background is geography and environmental science. I'm not a forester, I'm not an arborist, but I am a fellow tree addict. And I don't often get a chance to talk to people who work so much with trees, who spend so much time with trees. But the way I approach trees is largely looking at the tree ring records and the stories that trees tell me from the rings, the annual rings that they have. So I'm going to tell you a little bit about the background of tree ring science, and then I'm going to talk a bit about my research in maritime coastal forests of New York and New Jersey, and I'm also working a little bit in the Catskills. So just to start, typically tree ring scientists, we travel to very remote regions around the globe, pretty far-flung places, and we are looking for long-lived, climate-sensitive trees, which means I've spent a lot of time working in the boreal forests, up in Alaska, across Canada, and in Central Asia. You see that map? And the little green dots are just tree ring sites from around the world. And I've spent a lot of time going around the northern hemisphere to these kind of remote areas where trees aren't very disturbed by people. So that can be several weeks in the field, backpacking or flying in. This is a little bush plane that took us into Wrangell St. Elias, a national park in Alaska, where we were looking at 500-year-old white spruce trees. But more recently, I have been looking for sites more locally because I work with students. I run the environmental science department at William Patterson University, where I'm with wonderful students. I love this picture because I can turn them into tree huggers. It's really a wonderful job, but as you probably know, there aren't lots of old growth forests in this area, right? We have a long history of development and cutting trees, but there are pockets here and there, which I will talk about. So just a little bit about methods. The tools I use are, it's an increment borer, it's a hand drill. Just wondering if any of you use these at all. Yeah, okay. So it's a steel hollow threaded drill, and we take samples out of trees about the size of a pencil. It's relatively non-destructive. Sometimes, if people are very concerned about the trees, we might dip them in alcohol when we core between tree to tree, but by and large, we don't fill in the hole. The tree will naturally fill itself in. No, that's a little debatable with people. But then once we have samples, we take them back to the lab, stand them up so that we can see cellular detail, and then we're putting exact calendar dates on each individual ring. So you can see the bark. These are core samples. You can see the bark, and then the rings that go all the way back. So for a site, we would typically core 12 to 30 trees, 2 cores per tree, because we're trying to get at a stand level understanding of growth, right? Any tree can have individual disturbance. They're living organisms, recording everything in their environment. So generally, we're trying to avoid disturbance, like competition between trees, or if a tree got struck by lightning. We've even seen trees where animals use them to, like bears might use a certain tree to scratch, or moose can use them to rub their antlers. So we avoid ecological disturbance like that as much as we can so that we can isolate a climate signal. And then what I'm looking at is, in general, annual ring width of tree rings. So you can see some variability in the tree rings. Some of them are wider, some of them are quite narrow, and it gives us information about what the growing season conditions were like for as long as the tree was alive. I don't know if you've all saw, in the past couple days, the New York Times had an article about this 4,800-year-old bristlecone pine growing in California. So that's almost 5,000 years of understanding of climate variability through time. So when we're looking to understand temperature variability, we often wind up in the northern latitudes or high elevation. So you can see the tree core on the bottom. You can see variation in individual ring width. At high elevation, like where tree line is, or up in the northern latitudes, like in Alaska or Canada or Siberia, those rings are reflecting temperature. Trees aren't growing any higher than tree line because it's too harsh and it's too cold. So they're very sensitive to changes in temperature. So in those places, when I'm coring trees, I can learn a ton about temperature. And in those remote places, trees can live 800 years, maybe, Siberian larch or white spruce. So we can create these long records of temperature. So my colleagues and I, my lab at Lamont Doherty, and colleagues from around the world, we're actually a pretty small community, the tree ring community. But we've worked so you can see this map, you see the dots on the map. These are tree ring sites around the northern hemisphere, and these are sites that generally span more than 1,000 years. So there's not a ton of them, but based on these old tree ring records, we can create long reconstructions of temperature. So you can see this 1,200-year temperature reconstruction of the northern hemisphere. So that's all based on individual tree ring years. And all the way to the right, you can see recorded temperature for the past 100 years or so in blue, right? And you can see a warming trend in that recorded northern hemisphere temperature data. And then the tree ring records adds 1,200 years of context, right? So all of a sudden you can ask questions like, have we seen warming like this over the past 1,000 years? How often does it last? And you can start to look at where it's happening. I know it's kind of early in the morning and I'm going to throw a lot of graphs at you. I'm really sorry. I love looking at data. Okay. Thank you. My poor students. By the end of the semester, though, they really, I tell myself that anyway, they enjoy it too. Okay, so why do we do this, right? And I'm using an example from Mongolia because I've done a lot of work there. It's what I did my dissertation on. But in many places of the world, there's very few meteorological records. So for us to really understand how the climate varies naturally, we need to be looking at something. And if we're only looking at 50 years of data, it's really just not enough information about what the natural climate system can do and how it can change. So you can see this is a map of Central Asia. I have a circle around Mongolia. And really what I want you to notice is that from the 1800s up to 1930, there's no records at all of meteorological data, temperature, precipitation, those types of records. And then up to 1950, there's 10 records. I mean, Mongolia is huge. It's the size of Alaska. And then up to 1990, there's 37 records. So to me, that's almost no data, right? So tree ring records, we can actually, Mongolia is this incredibly arid place. Trees are super sensitive to moisture, and most people think of Mongolia only being steppe and drylands, but there's actually incredibly pristine forests there. You'd be surprised. It's a very natural country, and we've been able to develop a network of tree ring records and reconstruct drought there, going back almost 2,000 years, but that's best case scenario, maybe about 400 to 500 years. And then once you have those records, again, you can start to answer questions like, how often do these droughts happen? How long do they last? Have you all been hearing about megadroughts? Megadroughts in California and the Southwest, right? Megadroughts was a term that the scientific community has been using for a long time, and I'm just starting to see it more in mainstream media. But this is where droughts can last, decades, which we see from the tree ring records, and now we're seeing in real time in California and the US Southwest. So this is actually really cool. Trees in these extreme environments can fall over and land on rocky areas, and they don't rot. They'll rot a little bit, but it's pretty slow. So what we find is we call them relic or subfossil trees, and they can sit out there for 1,000 years, believe it or not. So by combining records of living trees and dead trees, we can actually develop records that go back thousands of years. I think the best case is in Europe, about 10,000 years. But so to us, these subfossil relic trees are like gold. Tree ring scientists get really excited in the field when we find samples like this, and they just look silver weathered and kind of beat up. And that's when we have chainsaws. That's really the only time we're cutting trees, is when they're already dead. Otherwise, we're using those hand drills. Oh, and the picture to the right is another example of subfossil trees, but you can see these stumps growing out the side, and that's actually a volcanic ash. It's not snow. So it's a huge volcanic eruption that happened that killed trees in 800 AD, and then they were preserved. And then as the stream bank erodes, we take samples, and then we have these dead sections, and we can combine living and dead trees to make records that go back, 1,000 years or more. So one of the most important products, and I put products in quotes because it's a paper. Our products are published papers, right? But one of the most important products that came from the tree ring community is something called the Drought Atlas. And we have a drought atlas in North America. There's one for Asia, and we're working on one for South America. But those red dots on the map are all tree ring sites, the larger red dots. And then you can see the smaller gridded dots underneath. So any of those grid points, you can download data on droughts for 800 years or more, up to 2,000, public access. So it's underlying tree ring data. So just imagine, there's 868 sites. The data spans 800 to about 2,000 years. Imagine if you're a manager, water manager, where all of a sudden you were looking at 50 years of data and look at 800 to 2,000, how that might change the decisions you're making. Though, getting the work that we do into the hands of decision makers is a whole science unto itself, right? That's a really challenging thing. And actually, scientists aren't really great at that. All right, so you might be interested in some of the oldest trees that have gone into this drought atlas in this area. I'm curious if you have any ideas of where some of the oldest trees are in the New York, New Jersey area, and how old they might be. Any ideas? So we've had people working the pine barrens, and I do think they can get to 300 years or so. The oldest pitch pine is up in New York State, southern New York, over 300. So often people think trees are very old. They can be very big, but sometimes the big trees are just growing really fast. So old trees, you may all know this, they often look stunted and gnarly. They look like old people. And they're probably not commercially very valuable, and that's why they're still around. So some of the oldest trees that I've seen come from Hutchinson Memorial Forest, which is near Rutgers. Those are white oak dating back to the 1650s. I was there a few years ago trying to resample and update that site, and I think the oldest trees blew down. So my colleague, who is the director of the Tree Ring Lab now, in the 1980s went all over, coring everywhere in the Northeast, and he sampled this site in Hutchinson, and that's where he found the trees from the 1650s. But going back, I think the hurricanes we've had over the decades has just taken them down. So they went back to the 1700s, but the really old trees, I think they're down. And these were not the stunted-looking trees. These are beautiful, large white oaks, very commercially valuable, and it's very odd that they're still there because I think a lumber company owned the property. Okay, and then in West Milford, there's some chestnut oaks growing on a ridgetop that are super gnarly. They date back to the 1500s. And just yesterday, I got dates from hemlock trees from the Catskills. I'm super excited. We have some trees that date back to the 1500s. I'm also pretty shocked because they seem like they were growing fast. But again, this is rocky ledge area, so the growth is very slow, and they're protected potentially from fire and maybe logging, though I'm not totally sure about that. And then there's other hemlocks near Minnewaska that date to the 1650s as well. But when we're doing tree ring paleoclimate stuff, I am looking for old trees like this in this area. And they're not easy to find, but I have a feeling a lot of you might know where some pockets might be. All right, and then just one of the most poignant examples of why tree ring records are important. Paleoclimate records are important. So I do tree rings. There's other paleoclimate fields, like people look at ice cores and corals and sea sediments. So all looking at how these layers change because of environmental conditions. But from tree rings, one of the most important examples is the Colorado River Compact that happened in 1922. This is when 7 states divvied up the Colorado River. And I'm putting up another graph. And really what I want you to see, the blue black line, the black line is tree ring records, and the red line is observed stream flow. And it's hard to see where you see that arrow pointing to observed. That's the 1920s. So that stream flow you can see is really high. It's high flow. There's no data behind it. They just didn't have it. So at 1922, I mean, you can see that point in the observed record around 1920 was probably the highest flow of the past 1,200 years. And that's when they divvied up the water of the Colorado River, right? So when it was wildly high and not representative of how the river actually would normally look. So the way they divvied it, the Colorado River could probably never meet the demands that they would need. At the time when they divvied it up, the demands weren't very high, but they're surely high very now. I imagine you're all hearing on the news about Colorado River and Lake Mead and all the problems with stream flow right now. And it's worth mentioning that Mexico wasn't even considered in 1922, even though it drains in Mexico. So, one other thing to notice, if you look around right before maybe the 1150s, you see this period of drought that lasts a decade or more. Can you all see that really low point right in here? So this is something we wouldn't know from meteorological records, that drought can last more than a decade, right? It's important information. Okay, and I'll show you this area, a reconstruction of drought based on tree rings for the Hudson Valley. And I imagine many of you know about the 1960s drought, 65, 66 was the drought of record for this area. Water managers use it to try and understand how low flow can be in this area, but it was the driest time of the past 400 years, which we know from tree ring records. Since that time, we're getting more precipitation in this area over the past few decades, so there is a wetting trend. But we have to keep in mind that droughts like that are possible. Okay, and this was more for me than for you all. This is bragging. This is me bragging. So what I want you to notice is tree ring growth is the solid gray line, and recorded drought data is the dashed line, right? And can you see how well tree rings record drought? Can you see how close the relationship is? It's pretty amazing. And I actually would say, and I bet you all would agree with me, that the trees record drought better than the meteorological data, right? Because they're in the environment responding to all the complex layers of soil and evaporation. So I think they're actually a better recorder of drought than our meteorological records. But all this to say, our records are really strong, and also our records are exactly calendar dated. So we know the climate exactly. No mistakes. We can't have mistakes. Our whole science is based on accuracy. Oh, so are you impressed? Yes? Okay, good. I was like, wait, are they going to like that, or are they going to hate me for showing a graph like this at 9 in the morning? Okay, so I have another project in the Catskills that was recently funded by National Science Foundation, and I'm trying to extend that record. And I wasn't really sure if there are going to be very old trees in the Catskills. And I'm working with a group of foresters up there, and they've identified 10 sites that they think are worth looking at. So we've gone to a handful of them. And what I'm finding is they're right. You saw the dates back to the 1500s, and other trees that I've cored there go over 300. So it's very exciting. And I imagine that you all know that we rely on the Catskills and Delaware watersheds to supply water to New York City. Visionary people realized that by just preserving forests up in the Catskill region, we'd have high quality water for New York City for generations. Really unbelievable land use and planning that occurred then. And those forests are actively managed, and you probably all know that. But so what we're hoping to do is generate more records from there that go back longer to understand drought in the Hudson Valley and how that might impact water resources for New York City. And I'm also working with another paleoclimate scientist who studies lake cores. And he took a core from lake sediments, and using various techniques, looking at seeds and looking at chemistry, he can reconstruct drought as well. But his records go back to when there were glaciers here. So to the very end, which is about 12,000 years. So we're going to combine tree ring records and his lake cores and try and get a reconstruction of drought that goes 12,000 years. And then, of course, it's also engaging students and public audiences on the work that we do is part of why we get funded to do it. All right, and some other applications of tree ring science. There's so much that we can do with tree rings. Mostly we do paleoclimate reconstructions. That's kind of the bread and butter of tree ring science. But there's other applications. And fire history is one of them. So, and this we've even done somewhat in the Pine Barrens, though it's not published. Really seeing how incredible creating fire histories from tree rings is mostly in the US Southwest, where the trees out there are so old, and I'm sure you all hear about the fires that have been happening out there. But low-grade fires come through, they burn trees. As long as they don't kill them and burn them up, they can leave fire scars. And so the trees are actually recording. You can see the scars with the years on them, and you can actually see that burnt outer layer, and then the tree just heals and grows around it, but it leaves this incredible record of fire. So we might know about fire through records over 100 years, but we really have no understanding of how often fires happen over 1,000 years, and that's really important information for managing and development. So, fire history. We can also develop insect outbreak records. And this happens, we see this quite often. So typically we avoid trees that have insect outbreaks because we're trying to focus on the climate signal, and I would view insect outbreaks as a disturbance. But sometimes we might want to focus on insect outbreaks and look at the frequency and how long does it take trees to recover. So again, we would be comparing these to like records of outbreaks. So we could see it in the tree rings, and then we would extrapolate backwards, right? So this is kind of a signature that you see in the tree rings. You see it's growing really well, big rings, and then it just gets hit. It might have a missing ring, and then it takes years for it to recover. That's kind of a signature that we see in tree ring patterns for insect outbreaks. And this is western spruce budworm. This is a Douglas fir. And there are papers on insect outbreaks that I could point people to if you were interested. The other application of tree ring science is archaeology, dendroarchaeology, and this is actually how the whole field started. This is Pueblo Bonito, Chaco Canyon in New Mexico. So for construction of these pueblos, the cliff dwellings, they use timbers, and those timbers are pretty well preserved. So scientists in the 1920s, the person who started tree ring science, his name was A.E. Douglas, he would cut these timbers and he'd compare them, the growth patterns, to living trees. And if they overlapped, you could put an exact calendar date on the year the tree was felled to build the pueblo. So that is how all the pueblos in the US Southwest are dated. It's how we have a history of them. But then they also realized that this is amazing information for climate variability and understanding how, in this case, drought varied through time. And this is more recent. Under the World Trade Center site, they found a ship. Did you all know that? No, okay. There was a ship down in the debris, and I believe they think it was put there just as filler, that they put lots of garbage and stuff in there before they filled it. But, so tree ring methods, our lab was contacted. We were able to take cross-sections of these trees. It was white oak and hickory. And then what we're doing is provincing. We're trying to figure out, this boat could have come from anywhere. So we would compare the records to tree ring records just across the world. And what we found, so the World Trade Center ship is that black line, and then we compared it to chronologies all over, but it turns out that this was from the Philadelphia area. You can see it locks in the patterns, the growth patterns lock in pretty well, quite well, statistically significantly. And so the cut date was 1773. Right, so just a really interesting, we do lots of archaeological work. I've worked on violins. Everybody thinks they have a Stradivarius. So really, they're very upset when I tell them they don't. And that's only because I can tell if the tree ring patterns on a violin come from a region in Cremona, Italy, where the timber would have been taken from. The last year, I can tell the last year on that violin. There's no bark on a violin, obviously, but I can tell the last year. So I can give them a sense if it came from that region or not. It usually does not. And they still have to pay me. It was very tough work. Okay, so switching gears to maritime forests. More recently, I've been going less off to far-flung places, and I've been working more regionally, which has been wonderful, because I need sites to bring my students, and also it's much easier. I have teenagers. It's hard to leave them for a month to go to Mongolia, but though they would love it. But I saw some papers come out in 2018 that showed that tree ring records are capturing a signal of tropical cyclones or hurricanes, just call them hurricanes. And that's because hurricanes come in and they damage trees that might snap their branches or shake up their roots, and the following year they have less growth that they put on because they're recovering. But that's a record of hurricanes. And you might have heard hurricanes are getting stronger, or we're going to have more hurricanes. We don't really know that much about hurricanes and hurricane history. I think the records only go back to the 1850s, and they're not great. So tree ring records, I've told you in this area, some trees we know go back to the 1500s. There's potential to build a record of hurricanes in this region, which would be really fantastic, very applied science, which I really like. Could be used for managers and to also understand, we need to understand the past to see where we're going in the future as well. So when I read these papers, they came out of Mississippi and Virginia. I, of course, thought about our maritime forests in New York and New Jersey. There's just little pockets of them here and there. I'm thinking about Barnegat Light at Long Beach Island. There's like this tiny little patch of coastal forests near the lighthouse there, but they're incredibly dynamic forests. And the more research I did on them, the more literature I found that there might be some 300-year-old coastal forests in New York and New Jersey. Of course, I never believe the literature. Everybody thinks they have old trees, and they usually don't, but it was worth investigating. So most of Long Island is developed, but places like Fire Island and Montauk and even parts of Gateway National Park and Sandy Hook have some protected forests. So that's where I started. So here's, and I should just say, this map on the left, it just shows you where coastal forests are. So really just a couple 100 feet from the beach, right? They're really just behind the dunes, these forests. So they're constantly being bombarded by salt spray, some saltwater inundation. It's a pretty harsh environment. And this is oak, holly, cherry, nyssa, red cedar, right? So pretty diverse, growing in sand, really interesting forests. So there's a park, 3,000-acre preserve in Montauk. Montauk, I hadn't spent much time out there. Pretty amazing, the forest tracts that they have there. I was kind of stunned considering how much development we have in New Jersey. So we cored these in 2018. These date back to the 1600s. This is the same story where my colleague sampled them in the 80s. They dated back to the 1650s. I can't find any trees that old. But I have his data, so I can combine it. So these are the goals of this project. I'm trying to understand if these forests are recording that hurricane signature. And if so, can we improve the record of hurricanes, the history of hurricanes? And then, well, part of the reason why I'm here and why I'm interested in connecting with a group of like New Jersey Shade Tree is because the information that I generate also informs how resilient trees are to extreme events and how vulnerable. So I'm really interested not just in creating these paleoclimate records, but also trying to understand how fast do they recover, how vulnerable are different species, because coastal forests are getting hammered, as you probably know. There's a pretty lot of sea level rise and tough things happening there, and I think there's going to be a lot of restoration and conservation efforts, and I think our science can inform some of that work. So this is what my chronology looks like. This is a growth chronology from the mid-1700s up to 2000. It's just based on about 20 trees. And what I find is that the growth it's negatively related to sea level rise. So as sea level rise increases, tree growth decreases. And I'm not totally sure what's happening there yet. What I think is happening is that sea level rise is raising the water table on barrier islands. I'm not a hydrologist, but I know some. And I think what's happening to some trees is that they're drowning from too much fresh water. There are wells on some of these sites, but they don't work all the time. They break a lot. But that would give us information about the water table and also if there's saltwater intrusion coming into these trees. So there's actually a lot of work to be done. But this graph, the take-home message from this graph is that sea level height is negatively impacting these forests out in Montauk. Just so you can see what sea level looks like from the mid-1950s up until now. I imagine you've all seen ghost forests in New Jersey in the coastal areas. The very famous artist Maya Lin recently did an exhibit on ghost forests. She took some of these trees down and brought them into New York City as an exhibit on climate change and climate impacts. Okay, so then my question about if these trees are recording hurricane signals, I took 100-mile radius around the site, and I just figured out what were the strongest hurricanes for as long as the record is old. A lot of these might, sorry, you actually can't see the years, but it's like 1944 and 1960. These are huge hurricane years. And what I found is that, you don't even have to look at that, sorry. It's like, what I found is that it's growth anomalies, right, and the year of the event. So the bottom line is year of the event, year 0. And you can see the growth is negative in the year after the event, which makes sense to me. Hurricanes happen in August or September. Trees are pretty much done growing by then, so you don't see the effects until the next year. But they're definitely recording tropical cyclone signal. So that's really exciting. I have to publish this. It's like on my top of my to-do list, and I can never get to it. But the other interesting thing I think that from this graph is that you can see the growth comes right back up after a year. So there's definitely some resilience from these white oak trees growing on Montauk. Doesn't mean that all species are going to have this resilience, but they do here. And then there's other trees that I want to investigate in Montauk as well. Holly, Ilex. Okay, And then from these barrier islands in Sandy Hook and the sunken forest in Fire Island, this is all national park. I've been working with the National Park Service. They have tree ring sites. They have forests, holly forests that we explored because they said they were quite old. So holly hasn't really been used in tree ring science, and I think some of the reason is because the conditions are so harsh growing there. There's catbrier, and there's so many ticks. It's pretty hideous field work. We actually wear hazmat, white suits when we go work in there. And also the rings of holly, that bottom picture is a core, and you can see how light the rings are. They're very difficult to work with. So most people thought they didn't work as a tree ring, that we could put exact calendar dates on each year, but it is working. So far, these are our tree ring chronologies that we produced, one from Sandy Hook, and you can see they date back to the 1700s, which is pretty good for trees growing in national parks and forests that have so much pressure on them. So 1796 and 1825 is how far they go back. So it's not super long like the trees I was telling you about that date back to the 1500s, but even hurricane records that spanned 300 years, that doubles our current understanding. So it's valuable. And one thing I want to point to is that the trees from Sandy Hook, you can see this really, I can't even reach it, negative growth. So they were just hammered by Sandy. The holly trees in Sandy Hook, a bunch of them died and didn't recover, and the ones that did survive, the growth, you can see the growth hasn't come back up yet. So I want to investigate the resilience of the trees, and it could just be a difference of a foot in elevation or the water table. I'm not really sure. But what I do notice just anecdotally is that the holly is recovering in terms of all the seedlings that are coming up. So it looks like that forest is going to replace itself over the next few decades. Okay, and just these forests are considered highly vulnerable. A great study that came out by the USDA Forest Vulnerability in 2018, and it talks about how these are the most vulnerable ecosystems in the Mid-Atlantic region, and there's been significant dieback already. Just to give you some numbers, in the Chesapeake Bay, the dieback has been 0.5 meter to 6 meters a year. In the Delaware forest, they've seen the forest marsh ecotone, where the forest meets the marsh, migrate 141 meters over 76 years. So they're vulnerable, and changes are already happening to these forests. Okay, and just so you can see, I put sea level rise information in Sandy Hook and New York. The story's the same, it's 1C, right? If it's rising in Fire Island, it's gonna rise in Montauk. But what you can see, this is a holly and Nyssa sylvatica forest, and you can actually see the water table coming up. You see it's a little bit wet, and the trees that are a little bit lower are dying. And the Forest Service tells me that they see this water coming up a little bit more every year. So we have instrumented these trees. We have dendrometer bands on them, which is giving us almost real-time information about how they're responding to extreme events. I think we get growth every hour on these trees. And then we also installed, they're called pin dendrometers. We also installed our own meteorological station out on the beach in Fire Island. So we'll get information about when they start growing, when they stop, and how they're responding to extreme events. And that data will be live. I haven't paid the bill for it yet, so it's not live yet. It's like $60 a year, but I will. Okay, so Next steps for this project is there's a lot of other sites that I'd like to get to, North Carolina, other sites in Long Island, Massachusetts. I'd really like to build a coastal forest network of trees and tree ring sites. And then there's a bunch of species that I'd like to look at. How are individual species responding to climate extremes and climate change? And then really drilling down more on how I quantify resilience and vulnerability. And that's what managers and the Park Service really want, the information. That's the information they really want. How vulnerable are these trees? How resilient are these trees? So I think we can do that with tree ring records, but it's, typically it's moving more into the applied field, which I'm really happy to do. And then, of course, publish the work, connect to decision makers, and really broaden our education impact. All right, and then I just wanted to mention that I built a website on tree ring science for undergraduates, and it's all intro to dendro, and you can drop into our sites and look at data. If anyone's interested or works with students, it's public, and the link is in there. And then I have a bunch of collaborators, science. We always work in teams, so I listed them and just put some pictures of my students out in the field doing some work. But thank you very much for your interest and attention. I'm happy to take any questions. Yeah. Do you want me to do the questions or? Yeah, okay. Yes. Yeah, we do. It's really interesting information, and I think I had a colleague who was studying damage through resin ducts. He would find that when trees would get damaged, they'd have resin, and it would show up only on maybe the south side of the tree. So we do record that information. Yeah. He was asking about if we record the direction we take the core from, because if a tree is facing the sun or facing the shade, trees don't always grow evenly around the whole bowl. But for what we find, trees in kind of extreme environments, it's very based on microclimate and the rocks, or if they grow some reaction wood or something like that. So I haven't always noticed the south side or east side is bigger, but at least for the forests that I work on, which I'm sure can be different from what you all are working on. I'm always looking for stressed trees growing outside. They're usually pretty happy with lots of water and good temperature and good soil. Those trees, the rings are kind of complacent, and I avoid them. So I'm looking for kind of stressed trees. They grow slower. They have more climate information. Yeah.
Recently done work on the California redwoods. I was doing some studies. I don't see any information on that. Have you done any research on the redwoods at all? Because they date back several thousand years. I know some of the ones I've been doing.
So I haven't. My colleagues have, but I haven't done work on the redwoods or the bristlecone pines. But they are used in those drought atlases that I put up the maps for. I mean, to be honest, tree ring, wherever there's old trees, tree ring scientists have found them. There was that bald cypress from Florida and the southeast coast. I think there was an article on that recently. Dates back 2,000 or 2,500 years. So one of the oldest organisms in this area, the East Coast. Yeah. Yes?
You talked about temperature and rainfall separately. Can you determine?
Yeah, so for temperature, we typically go to sites where the trees are limited by temperature, which is the northern latitudes, the tree line or high elevation. And for drought, likewise, we go to sites where trees are limited by moisture. So you can think of the whole US Southwest is so dry that those trees, juniper and pinyon pine, they have a very strong, their rings reflect moisture, growing season moisture conditions, largely. It's the dominant factor. Of course, there's always going to be some temperature and some other signals mixed in, but we're trying to isolate the limiting factor, either temperature or precipitation, by going to the sites where we know that's the main factor limiting their growth. Right, and so in this area, trees growing on a rocky outcrop can be limited by moisture. They can be very moisture sensitive just because of the substrate they're growing on. Right, so for example, hemlock trees growing right at the Mohawk Mountain House, right behind in Minnewaska, New York. They're on a big rocky talus, and those were some of the best trees for a drought signal in the Northeast. That's actually what brought the tree ring community started in Arizona, is the biggest lab, but those trees in Mohawk brought a new tree ring lab up to the Northeast because we saw all the potential for temperature reconstructions in northeastern forests. And there's whole groups of scientists who work on ecology and are using tree rings for ecological studies, understanding how forests are recovering. That's hasn't been my focus.
Have you done any work along the Kittatinny Ridge? Because up there, you have pitch pine, which is a little unusual. A lot of people don't understand that there's pitch pine in the northern part of Warren County, the southern part of Sussex County. They find it a little out of place, but it's, a fire regime up there.
So it's on my list. I've hiked up there a bit, and I've noticed those forests. And then I've done some work in High Mountain. There's incredible Atlantic white cedar swamp forest up in High Mountain, and that dates back a couple hundred years as well. And because it's in a bog, nobody logged it. You all know how important Atlantic white cedar is. People poach those trees, but there's an incredible forest up there. So I've done some work there. But pitch pine, I'm very interested in pitch pine. It's very hard to work with. It drops rings. Not around the whole bowl because it would be dead, but in certain spots it just drops rings all the time. We call them missing rings, and it adds rings that aren't actually annual rings. They're just what we call false rings. So they're kind of torture to make students work on them. Otherwise, I'd have more sites. But yeah, they're very climate sensitive.
Can I ask a basic Class 101 question?
Please.
And that is, I understand fat rings, skinny rings, and stuff like that, but maybe could you expand a little bit on what you observe, what you measure to draw your conclusions? I understand occlusions like for fire and stuff like that, but how do you make this leap to
that's
interpretation?
A good question. Thank you. So mostly we're looking at ring width, right? Measured at a thousandth of a millimeter. We spend a lot of time on microscopes. And so we have a record of growth, and it can vary tremendously from ring to ring to ring, where a ring can be 0.1 millimeter. 0.1 millimeter or less, down to the thousandths of a millimeter. Rings can be very narrow, and that's reflective of the growing season condition. But what we do, and this is actually what sets us apart from many other paleoclimate fields, is we can compare our data to recorded meteorological records like I showed you. So it's calibrating our tree ring record to the meteorological data. So I can say, these trees are recording drought because they're growing in this dry area. And I know the ecological conditions, and I have a good idea of what the limiting factor of growth is, and it's moisture. But then I can compare it to meteorological records, and I can say with statistical certitude, right? These trees are recording 70% of the drought record that's in the meteorological record. So I can, and we do that. We tell you how strong the trees are recording drought, right? And then based on that relationship between tree ring growth and meteorological records, then we can extend backwards, right? Now we can say this tree ring record is reflecting moisture, so we do a regression analysis where we change the tree ring record into a drought index rather than millimeters based on the relationship with the recorded data. Does that make sense?
I have a question with regards to John Day, Oregon, if that happens to be one of the places that you have looked at. I don't know if you've been out there.
I have not. I haven't.
It's amazing. I was out there back in 2014, and the climate change that has occurred over the millions of years, it's gone from volcanoes to there's 1,500 feet of volcanic ash on top of the mountains there. And
so there's a lot of studies of, I didn't put a slide up, but we also do volcano histories. Tree ring records around the northern hemisphere, they all record major explosive volcanic eruptions because they're so big, they cool temperature the following year. So the big volcanoes, 1816, 1783, 1500, 1257, they all, it's like you can just, there it is, you see it in the tree ring record. It's a really narrow ring, so we can reconstruct volcanic activity as well. But in Oregon, also earthquakes. We can do the same thing with earthquakes, trees growing on fault lines. And there's a lot of people in Oregon and Washington area who work on trees to reconstruct earthquake activity. In some cases, the earthquakes have been so huge that they sink the forests, they go underwater into lakes. So all those trees, the death date is when the earthquake happened. So that's some research that people are working on right now. You know, there's no records of earthquakes that happened 1,000 years ago, but in that case, we need to work with trees that are very near where the fault lines are for them to shake up the trees enough so that they're damaged so that they record an event like that.
Could you please put the slide back up that had the website location?
Oh, sure.
Thanks.
And we're working on a new lab that talks about extreme climate and impacts on people, indigenous people and people from the Arctic through like oral histories and things like that. So that'll be exciting. Hi.
You mentioned the impact of earthquakes and how changes in the root system can be reflected in the growth rate. It reminds me in the pine orchard in the Adirondacks and the cathedral pine patch, also in the Adirondacks, one of the reasons they were harvested is because the frost heave is so significant, nobody was going to drag a log through it. Has anybody looked at those trees, and how do you reconcile the fact that cold frost damage could be impacting the ring, having nothing to do with temperature, warmth, or water?
Yeah, so I don't know the forest that you're talking about, but I think working...
I'll give you directions.
Okay. I think working with orchards is really cool, especially if the trees are old, because then you also could maybe get information about yield, which could be really interesting. But frost, we also, frost is really interesting because an early frost, it damages the cells. So that's when we see, there's an amazing, I took the picture out, unfortunately, but there's a beautiful image of tree ring records from 532, and it was a frost ring, and you can see the cells just kind of exploded. So we have records. We can, and that's actually a field that's growing, is called quantitative wood analysis, where people are starting to look at cellular detail for information about climate. And that 532 ring, it was a beautiful image with a scanning electron microscope. Columbia University sent it out as their Christmas card, which I was pretty excited about. Yeah.
I start off by saying thank you for all the insight that you provided, and this world needs more people like you.
Oh,
so
gosh.
thank you.
Thank you. That's really nice. It's a great job.
I could see it.
Yeah.
The question is about the data that's being collected by scientists like you. Is there a common database that being shared across all the scientists across the world?
So actually, thank you for asking that. The tree ring community is actually so fantastic at providing all their data. And actually, I showed you that I'm funded by National Science Foundation, and as a requirement, all my data has to be made public. National Science Foundation is public money. And it is also a requirement of journals when you publish that you make your data available. They used to give us like a year or two grace time because we need to publish other papers. They don't anymore. For us to publish, you have to make your data available immediately, which is kind of terrifying because it takes so much time to develop the data. And not everyone, sometimes people take your data and God knows what they do with it, but that's science. So all these tree ring sites, these green dots on the map, it's got to be several thousand sites. They are all available. It's called the International Tree Ring Data Bank, and it's run by NOAA. And actually, in the Tree Ring Expeditions website that I built, it gives instructions. What I do is I ask students to download the closest data to their house, and then just look at it and ask them questions about extreme events and stuff like that. So there's instructions on how to use the International Tree Ring Data Bank, but it's all available. And actually all the meteorological data, recorded temperature precip, you can get that in a couple clicks, which I also explain how to do in that website. Yeah. Thank you.